All right, so this video is designed to help you evaluate how you understand Newton's laws of motion and how it affects different objects. So I'm going to start off by quickly recapping the first two laws, and we'll get to the third one about halfway through, and then we'll finish off linking forces into energy. So the way you should use this video is I'm going to pose you a series of questions. So when I pose them, you need to pause the video, have a go at answering them, and then review it and see if you've got it correct, and then listen to the explanations as and when you've got them wrong. So let's start off with Newton's first and second laws. So these are things you should just know by heart by now. They are the bread and butter of physics. So Newton's first law, an object remains in uniform motion unless it's acted on by a resultant force. And in terms of what that really means, it means the velocity, both the magnitude and direction, of an object must remain constant unless it's acted on by a resultant force. And then Newton's second law, the resultant force acting on an object is equal to the rate of change of momentum. And we often express that in the form of this equation: force is change in momentum over change in time. And then we can get the most common form, F equals ma, but we get that by assuming that mass is constant. So those are our first two laws. Let's see how well you understand these two laws. Okay, so what I'm going to do is you've been given a series of force descriptions, and what you need to do is try and identify which description matches with the statement. So for the first one, which force would keep a sled moving towards the right and speeding up at a steady rate? And what we mean by speeding up at a steady rate is constant acceleration. So in this section of the assessment, you should assume that it's sliding on ice, so friction will be small, and it's traveling quite slowly, so air resistance can be ignored as well. So we're going to ignore all of those. So now what I like to do is pause the video, have a think, and then select which letter you think it is, and then we'll review it. All right, so let's take a look at this now. You've got your answer. So the correct answer to this question is B. And we're essentially using F equals ma here because the mass of the object is probably constant. So if acceleration is constant, force must be constant. And if it's speeding up, the force must be in the direction of travel of the sled, so to the right. So that's how we know it's option B. So let's give you scenario 2. So which force would keep the sled moving to the right at a steady or constant velocity? Again, pause it, select your answer, then we'll review it. Okay, so the answer you should have had is option D. So essentially, I'm just using Newton's first law here. So to go at constant velocity, the force acting on you must be 0 or no force acting. So the option should be D. Okay, so 3, the sled is moving towards the right. Which force would slow it down at a steady rate? Essentially constant acceleration again. So select your answer now. All right, so let's see which we've picked. So if you're going to the right, the force must be acting to the left. That's how you're going to be slowed down. And if your acceleration is constant and constantly negative, that must mean the force is constant as well. Okay, so scenario 4. Which force would keep the sled moving towards the left and speeding up at a steady rate? So select your answer now. All right, so let's take a look at what you should have. So again, we should have F. So if it's going to the left and accelerating or speeding up, the force must also be to the left. And if the acceleration is constant, the force must be constant as well. All right, scenario 5. The sled was started from rest and pushed until it reached a steady or constant velocity towards the right. Which force would keep the sled moving at this velocity? So select your answer. All right, so the force you should have selected is D. It takes no force to travel at constant velocity, or in fact, to travel at constant velocity, you cannot have a force acting on you, so that would be option D. So the sled is slowing down at a steady rate and has acceleration to the right. Which force would account for this motion? So select your answer. All right, so the answer you should have had is B. So the resultant force is always in the same direction as the acceleration. So if the acceleration is to the right, the force or resultant force must be to the right. And if it's slowing down, that must have meant that the object was traveling to the left. And if the acceleration is constant, the force must be constant. All right, so number 7, the sled is moving towards the left. Which force would slow it down at a steady rate? So select your answer. All right, so let's take a look. So this is the fourth one, B. So if it's traveling to the left and slowing down, the force must be to the right or in the opposite direction. The acceleration is constant, the force must be constant too. All right, so let's summarize some of the key things we've seen in action that you can bear in mind in future. So we've seen if the acceleration is constant, resultant force must also be constant. That's what Newton's second law in its form F equals ma tells you. And if the speed is increasing, so with just speed, not with direction, that means the resultant force must be in the same direction as the velocity if we're doing just one-dimensional motion. And if the speed is decreasing, that must mean the resultant force is in the opposite direction to the velocity. And then last thing, if acceleration is 0 or you're at constant velocity, the resultant force must also be 0. And these 3 rules apply whether we consider friction or air resistance or not, as long as we're talking about the resultant force acting on the object. Okay, so let's move on and have a look at some slightly different scenarios. So let's have a look at the scenario. So we've got a toy car. It's given a quick push, so it rolls up an inclined ramp, and we're going to be considering it after it's been released. So we're not applying a force anymore, and it reaches the highest point and rolls back down again, and friction is so small we're going to ignore it. So we've got a selection of statements about the net or the resultant force. And we've got 3 scenarios, so pause the video now and select your answer to 8, 9 and 10, and then we will review this question. All right, so now you've got your answers. So let's start with question 8. Well, to be honest, we can start with all 3 questions simultaneously. So let's first draw some forces on the diagram so we can see the forces that are acting on it. So there are 3 forces acting on this car. It's weight force, mg, and the 2 normal contact forces at the wheels. So the car is going to roll parallel to the hill. So the normal contact force is not going to have any effect on its acceleration. The only force that affects its acceleration is going to be the mg sine theta, or the component of weight force parallel to the slope. And the slope angle we can see is constant. And with the mass of the car, we're going to assume is constant. Gravitational field strength, we're going to assume is constant. So the force is going to be the same, regardless if it's going up, stationary, or down the slope. This force is constant, which means the answer to all of these is going to be A, because there's only one force acting to accelerate the car, and it's down the slope. All right, so let's have a look at another scenario. So we are tossing a coin straight up in the air, so we're dealing with one-dimensional motion. After it's released, it moves upward, reaches its highest point, and then falls back down again. Use one of the following choices, so you've got a selection of different force descriptions, to indicate the force acting on the coin in each of the cases described. And we're going to ignore any effect of air resistance. So pause the video, select your answers to these 3 questions, and then we will review them. All right, so let's take a look. So first off, again, drawing a diagram showing all the forces acting on the coin. There we go. So because we're dealing with it after it's released, the force we've used to push it upwards isn't acting on it anymore. So this is the only force, weight force, because we're ignoring air resistance. So the weight force is going to be constant and it's going to be downwards. So you might see where this is going. Option A is correct for all of them. There. So this is basically the same question that we had before, just in a different scenario. So it's the same principles involved. Okay. So now we're going to do some interpretation of scenarios and force versus time graphs. So you've got 8 different scenarios here, and you've got 8 different force versus time graphs, and you need to match the right graph to the description. So you are allowed to use the same graph twice, 3 times, as many times as you want, and some of them you will not end up using. So pause the video now and try and match the force graph to the statement. All right, so let's start with 14. So the car is going to the right, and it's going at constant velocity. So constant velocity means the force is 0. So we need graph E. That's what Newton's first law tells us. Likewise, question 15, the car is at rest, and we're assuming it stays at rest. So its velocity is constant, it's constantly 0, therefore the force is 0. So the car is moving towards the right and is speeding up at a steady rate. So constant acceleration means constant resultant force. It's speeding up, so the force is in the same direction as the motion of the car. So that's going to be option A. So the car is moving to the left, towards the origin, with a steady velocity or constant velocity. So constant velocity, force is 0. Straightforward. The car moves towards the right and is slowing down at a steady rate. So if the car is traveling to the right and it's slowing down, that means the force is to the left, or a negative force. And if the acceleration is constant, that means it's a constant negative force, which is B. The car moves towards the left and is speeding up at a steady rate, or constant acceleration. So if it's going to the left and it's speeding up, that means the force is to the left, so it's negative. And constant acceleration means the force is constant. So that is also B. The car moves towards the right, speeds up, and then slows down. So what is going to happen to the force? So when it's speeding up, the force will be to the right, or positive. When it's slowing down, the force will be to the left, or negative. So we're looking for a graph that's initially positive, then it's negative. That's option G. The car was pushed towards the right, then released. Which graph describes the force after the car is released? Well, if we released it, we're not applying a force, therefore it must be option E. All right, so let's move on to the next one. So again, exactly the same takeaways here. So those questions we just posed use exactly the same principles, it was just a different type of task. So again, these should be your 3 key takeaways that you should apply. And if you're still getting some of these wrong, it means you're not stopping and thinking about these 3 takeaways, because if you are, you can't get these questions wrong. Okay, so let's move on. So now what we're going to try and do is match acceleration graphs to descriptions. So you've got 5 different statements and a selection of graphs. Again, you can use these graphs multiple times if you want. So pause it now and have a crack. Okay, so first of all, the car moves towards the right, speeding up at a steady rate. So what that's telling you is acceleration is constant and it's speeding up towards the right, so acceleration will be positive. The car moves towards the right, but it's slowing down at a steady rate. So if it's going right, the force must be to the left, so the acceleration must be to the left and negative, but it needs to be constant to give you the steady rate. The car moves towards the left at a constant velocity. So constant velocity, force and acceleration are both 0. Car moves towards the left, but its speed is increasing at a steady rate. So if it's speeding up, that must mean the force is in the same direction. So the force is to the left, but force is constant to give you constant acceleration. That's B. So the car moves to the right, constant velocity. Constant velocity means resultant force is 0. And that's option C. Okay. So now we're going to think about the coin tossing scenario again, but we're going to think about it in terms of acceleration now. So what you're going to do is, for those 3 questions, pick which descriptions of acceleration you want. Okay. So now you've had a chance to have a go at these. Let's show you the answers. And you might notice it's a bit familiar to last time. So we're in exactly the same scenario. The force is downwards and constant. That means the acceleration must be downwards and constant. Acceleration is always in the same direction as the force and is directly proportionate. So if the force is constant, acceleration is constant too. All right. So now we're going to introduce Newton's third law because we're going to start dealing with two objects interacting with each other. So that's what Newton's third law is designed to explain. Newton's third law tells you how two objects interact with each other. And what it states is that every action has an equal and opposite reaction. So let's explain what that really means. So when two objects are interacting, so they might be having a non-contact force like gravity or electromagnetism, or they might be colliding and exchanging a normal contact force, for example. The forces they exert on each other are equal in magnitude. They're in the opposite direction, but they're the same type of force. That's what makes the Newton's third law pair. So the example I've given you is with gravity. So we have the Earth and the Moon, not to scale. And they would be interacting through gravity, which we usually call the weight force in mechanics. So the weight forces will be equal, they'll be in the opposite direction, they'll have the same line of action, as you can see there, but they'll both be gravitational type forces. So that's what we mean by a Newton's third law pair. So let's put that to the use. So we've got a scenario of a truck colliding with a car, and what we've got is a selection of descriptions about the forces that they're exerting, and we've got three scenarios. So it says the truck is much heavier than the car. So pause the video now to select which answer you want. All right, so let's take a look. So they're both moving at the same speed when they collide. Which choice describes the forces? Well, it's choice E. So Newton's third law says that two objects that are interacting will exert equal and opposite forces. So what you'll realize is you should have also answered E for 31 and 32. It doesn't matter what the mass and velocity are, the forces between two interacting objects will be equal, opposite, and of the same type. That's fairly straightforward. So let's change the scenario. So now we've got a truck and a car moving at this, and so what I'm going to do, so you've got the same choices as for the previous questions, so have a look back at those if you need to see what they are. Try and see which ones you want to pick for these ones. Okay, so for the first one, the truck and the car moving at the same speed, they exert equal and opposite forces. The truck is standing still when the car hits it, they exert equal and opposite forces. Hopefully you're getting the pattern by now. Two objects that are interacting exert equal and opposite forces. All right, that's what Newton's third law tells you. Okay, so now we're going to again deal with a car interacting with a truck. This time we're using a car to push the truck. So they're not colliding this time, we're using the car to push the truck. So again, we've got some descriptions of some forces. And what I want you to do is select the ones that match with 35 to 38. All right, so now you've got your answers. Let's have a look at what you should have. You should have A for all of them. So these two objects are interacting with each other, so the forces must be equal and opposite to each other. So you should have answer A for absolutely all of them. All right, job done. Okay, so we've got two students sitting in identical office chairs. Bob has mass 95, Jim has mass 77. And you can see Bob has placed his feet on Jim's knees and he's going to push away. So while the feet are in contact, so while the two objects are in contact, which of these would describe the interaction? All right, so the one you should have picked, E. They exert an equal and opposite force on each other. You've got two objects interacting. That has to be the case. All righty. So some takeaways from this. So it really doesn't matter how fast an object is traveling, how big its mass is. If you have two objects interacting, they have to exert equal and opposite forces on each other. It's one of those powerful and useful rules, but you have to wrap your head around that fact. Okay, so that's our takeaway here. All right, so in this question, we've got some velocity time graphs, and we want to match the relevant one to its description. So have a crack at that now, and then we'll review your answers. All right, so first off, which velocity graph shows the car moving to the right at constant velocity? That's clearly graph A. The velocity is constant, so that's graph A. Which velocity graph shows the car reversing direction? That's clearly graph F, because for a while velocity is positive, then velocity is negative, meaning it's changed direction. Which velocity graph shows the car moving towards the left at a constant velocity? So going to the left would mean you'll get negative, but velocity stays the same, so it's constantly negative. Which velocity graph shows the car increasing its speed at a constant rate? That's a straight line graph, so we're looking for option D. There, the speed is clearly increasing. All right. So I'm going to finish off by linking forces into energy. So Newton's laws help us describe force, acceleration, and velocity. Conservation of energy tells us how energy is exchanged from one form to another. So the law we're going to be using, energy cannot be created or destroyed, only transferred. And we represent that mathematically with this equation, that the work we do would give you a change in the kinetic, gravitational potential energy, or the elastic potential energy there. That's our expression of conservation of energy. And with mechanics, we often use the principle of conservation of mechanical energy, which states that if no external work is done, the mechanical energy, the sum of the kinetic GP and EP, must remain constant. And we often express that in the form that you can see there. So the sum of the energy to start with is equal to the sum of the energy at the finish. So let's put that into practice. So we've got a sled being pulled to the top of the hill. At the top, it's released from rest, so it's initially stationary and allowed to coast down the hill. And coasting means you're not applying any force other than the object's wave force. There's no external force. At the bottom of the hill, the sled has speed v and kinetic energy E. So we're going to ignore friction and air resistance in this, and you've got two scenarios that I'd like you to try and have a go at selecting the answer for. All right, so now you've selected your answers, let's take a look. So this is the principle we're going to apply, the conservation of energy. And it says it's coasting, so we're not doing any work, and there's no air resistance stuff, there's no work. So our change in kinetic energy, we half m final speed squared minus initial speed squared. It's losing GPE, so the change will be minus mgh. And it hasn't said it's changing shape, so we're going to ignore elastic potential energy. And all that tells you is the kinetic energy must be equal to the initial GPE. So it says the hills is the same height, so therefore it starts with the same GPE, so it finishes with the same kinetic energy. So that's 45. And if it's the same kinetic energy, it's the same mass, so it must have the same speed. So that tells us we should have picked option B for both of them. So let's finish off with a different scenario for energy. So again, we've pulled a sled onto a higher hill that is less steep. And you've got two scenarios. I'd like you to pick your answer. All right, so we're going to approach this in the same way using conservation of energy. And so it says that this hill is now higher, which means we're starting with more GPE, which means we're going to end with more kinetic energy. And if we have more kinetic energy for the same mass, we're going to have a higher speed. So we should have picked option A for the higher but less steep hill. Okay, so that concludes this video. So I just want to summarize what we've looked at. So Newton's laws are for when we're trying to link force, acceleration, and velocity. Conservation of energy that we've just seen is when we're trying to link the force, the velocity, height, and shape of the objects. And between these two principles, we can solve pretty much anything in mechanics, whether it's lower sixth, upper sixth, or getting into degree level stuff. We can solve it all using these two principles here. As long as we're not approaching the speed of light, then this stuff goes a bit weird. So this video essentially shows you what you should be able to do once you've finished the mechanics topics in A-level. These are the principles that you should understand, and if you can, you'll then be able to apply them effectively to other topics. So if you have any questions after this video, please feel free to comment and ask me. I'll get back to you as soon as I can. But thank you very much for taking the time to watch.